Dear students, today we are going to discuss the first topic of our first module, oscillations and waves. The topic is damped harmonic oscillator and its differential equation. So first of all, let us see what are the topics included in the first module. Your first module is oscillations and waves, and these are the topics included in the first module. So in today's class, we will discuss harmonic oscillation, damped harmonic motion and its differential equation. So before going into the details of the differential equation of a damped harmonic oscillator, we need to discuss how can we derive the differential equation of a simple harmonic oscillator. So first of all, let us see what is a simple harmonic oscillator. So the first topic as given in the syllabus is harmonic oscillator. A harmonic oscillator is any system that when it is displaced from its equilibrium position, it experiences a force called restoring force. So if we are considering a system, if the restoring force is the only force acts on that system, then we can call it as a simple harmonic oscillator. So in a simple harmonic oscillator, the force acting on that system is directly proportional to the displacement of the particle from its mean position, and it is opposite in direction. Okay, that is what is called a simple harmonic oscillator. So we can define the simple harmonic oscillator or the simple harmonic motion as if the acceleration of a particle, if it is proportional to its displacement from equilibrium position and opposite to it, then the motion is said to be simple harmonic. And as we know, it is described by sine or a cosine function, and we can write the equation as x is equal to a sin omega t or x is equal to a cos omega t. Now let us see how can we derive the differential equation of a simple harmonic motion. So simple harmonic motion, that is an example for a harmonic oscillation, or simple harmonic oscillator is an example for a harmonic oscillator. And in a simple harmonic oscillator, there is only one force acts on that system, and that is what is called the restoring force. Okay. So as I said earlier, the restoring force F is directly proportional to the displacement of the particle from its mean position, but opposite in direction. That's why we are putting a minus sign here. Now, if we are removing that proportionality constant, proportionality simple with a constant, then we can write that equation as F is equal to minus mu x. Okay, where mu is a constant and it is called force constant. And the negative sign in this equation, it indicates that force is always opposite to the displacement. Now, according to Newton's second law, we know that force is equal to mass times acceleration. Now, if we are writing the acceleration term in terms of displacement, we can write it as F is equal to m into d square x by dt square. Rate of change of velocity is acceleration. So velocity we can write it as dx by dt, rate of change of displacement. So while we are writing acceleration, a is equal to d by dt of dv by dt. That is nothing but d square x by dt square. Now consider that two equations. So in the first equation we have F is equal to minus mu x. Then according to Newton's second law, we have F is equal to m into d square x by dt square. Okay. Now equate the two equations. Then what we are getting? M into d square x by dt square is equal to minus mu x. On rearranging that equation, we can write it as m d square x by dt square plus mu x is equal to 0. In the next step, we need to make the coefficient of this d square x by dt square as unity. So for that, divide this equation m d square x by dt square plus mu x is equal to 0 throughout with m. So what we are getting is d square x by dt square plus mu by m into x is equal to 0. Where mu by m is a constant and we are putting it as omega square, where omega is nothing but the angular velocity of the system or the oscillator. So omega is equal to root of mu by m and it is the angular velocity of the oscillator. So we can write the equation as d square x by dt square plus omega square x is equal to 0. This is nothing but the differential equation of a simple harmonic oscillator. Okay. So in a simple harmonic oscillator, the only force acts on that system is the restoring force, and F is equal to minus mu x, and that is nothing but mass times acceleration. Then on rearranging that equation, we will arrive at the differential equation of the simple harmonic motion, and that is d square x by dt square plus omega square x is equal to 0, where omega is the angular velocity of the oscillator and it is equal to root of mu by m, or omega square is mu by m. Now, if you are writing the solution of this differential equation, we will have x is equal to a sine omega t plus phi. This represents the displacement at any instant t, and here in this equation phi represents the initial phase. A is the amplitude. Omega t is called the phase angle. Okay, so this is all about the differential equation of a simple harmonic oscillator. Now we are moving to the first topic in our syllabus, that is the damped harmonic oscillator and its differential equation. So let us see what is a damped harmonic oscillator. We need to consider a system or a body that oscillates in a medium like air. Then surely there will be some resistive forces that acts on that system. Okay, such forces are called damping forces, and this phenomenon is known as damping. So when a body oscillates in a medium like air, it has to work against these damping forces. So as a result of that, there is a gradual decrease in its energy. So the amplitude gradually decreases and finally the body comes to rest. Okay, so such oscillations with decreasing amplitude due to damping are called damped oscillations. Very important definition. Oscillations with decreasing amplitude due to damping are called damped oscillations. And due to damping frequency, the period of oscillations increases. If the frequency decreases, then period of oscillation increases. Okay. Now, let us derive the differential equation of a damped harmonic oscillator. For this, so we know that in a simple harmonic oscillator, there is only one force acts on that system, and that is the restoring force. So while we are considering this damped harmonic oscillator, there are two forces acting on that system. The first one is the restoring force, and the second one is the damping force. Okay, so as we know, the restoring force F1, here I am representing the restoring force as F1, that F1 is equal to minus mu x. And so restoring force F1 is directly proportional to the displacement of the particle from its mean position and opposite in direction. So we have F1 is equal to minus mu x, where mu is a constant and it is called force constant. Now the second force acts on a damped harmonic oscillator is damping force. Damping force F2 is directly proportional to the velocity of the system, velocity of the particle. So F2 is equal to minus gamma V, where gamma is a constant and it is called damping constant. Now here also this F2, the force is opposite to the direction of velocity. That's why here comes the negative sign. So in terms of the displacement x, we can write the velocity as rate of change of displacement. So F2 is equal to minus gamma dx by dt. Now, the total force or the resultant force acts on that system. We can write it as F is equal to F1 plus F2. In a damped harmonic oscillator, the two forces acting on that system are restoring force and damping force. So the resultant force F is equal to F1 plus F2, and that is equal to minus mu x plus minus gamma dx by dt. Now we know that according to Newton's second law, the resultant force is nothing but mass times acceleration. So as in the previous case, here also we are equating mass into acceleration, that is equal to nothing but F1 plus F2. So in the next step we can write it as m into d square x by dt square. Here also I have written the acceleration in terms of displacement x, that is equal to minus mu x minus gamma dx by dt, sum of F1 and F2. Now, on rearranging this equation 3, we can write it as m d square x by dt square plus mu x plus gamma dx by dt is equal to 0. Then the next step is make the coefficient of d square x by dt square as unity. For that, divide this equation number 4 throughout with m, the constant m. So after division, what we are getting is d square x by dt square plus gamma by m dx by dt plus mu by m x is equal to 0. Okay. Now I am putting this gamma by m, that is a constant. I am putting it as some constant that is equal to 2k. Gamma by m as 2k and mu by m as omega square. So finally I am getting the equation as d square x by dt square plus 2k dx by dt plus omega square x is equal to 0. This is nothing but the differential equation of a damped harmonic oscillator. This is the differential equation of the damped harmonic oscillator. So here in this equation, k is equal to gamma by 2m. 2k is gamma by m, or k is equal to gamma by 2m. That is the damping coefficient. And we have omega square is equal to mu by m. So we can write it as omega is equal to root of mu by m. That is the angular velocity of the system. Okay. So this is all about the derivation of the differential equation of a damped harmonic oscillator. In the next class, we will discuss the solution of the second order degree equation of a damped harmonic oscillator. So all the students have to write down these two equations, derivations, the differential equation of a simple harmonic oscillator as well as the differential equation of a damped harmonic oscillator to your notebook. Okay, thank you.